You can also come across rational functions that are not in the form that we looked at in the previous video. And these ones will be in the form where there's a derivative on the top and a function on the bottom. Now I've got here, I've called this the reverse chain rule, but in class I refer to it as integrating with feeling. And that's mainly because you've got to look at the function and realize what type of function it is, and then figure out what is more important. So using your gut, which is why I've called it through feeling. Now, in terms of what this will integrate to, we first need to look at if we had an example function where y equals ln of some sort of function of x. Now, when we differentiate this function, we'll get dy dx is ln differentiates to 1 over the bracket times by the derivative of the bracket, so times by f dash x, giving you f dash x over the function. Which means if you were to integrate this, this type of function is going to go to ln of the denominator plus c. So really, if you get a fraction and there are variables on both the numerator and denominator, you should be checking to see if the derivative of the denominator equals the numerator. Now, in all of these examples, we have that. So in number 1, we've got 3x squared minus 2 over x cubed minus 2x. Well, in this case, the derivative of the denominator is exactly the numerator. That means that we can integrate with a log. And so we're going to get, now when I do this, I'm actually going to sort of ignore the numerator for now. And I'm going to pretend that this is 3x squared minus 2 all times by 1 over x cubed minus 2x. And the reason I do that is, now this method is a little bit informal, but it works, but it only works if the derivative of the denominator is either the numerator or the numerator times by some sort of constant. So I'm going to just look at this part here, and I'm going to integrate that. So I get what I had before, 3x squared minus 2 times by ln of x cubed minus 2x. And then when you integrate, you've got to divide by the derivative of the brackets. So I'm dividing by 3x squared minus 2 plus c. On our left part of this, those completely cancel, and we're left with the answer of ln x cubed minus 2x plus c. For number 2, again, I can look at this and I see that the derivative of the denominator is 2x, the numerator is 6x, so that I can multiply my derivative of my denominator by something to get 6x. Now you might be able to very quickly figure out that it's 3, and so therefore the answer will just be 3 ln of the denominator. But if it was more complicated and you weren't quite sure what that was, then we're just going to follow these steps. Again, rewrite this as 6x times 1 over x squared minus 9, and then we're just going to integrate the fraction part. The 6x stays where it is, times ln of x squared minus 9, and then divide by 2x, divide by the derivative, plus c. The x's cancel, and 6 divided by 2 is 3. We're left with 3 ln x squared minus 9 plus c. Number 3. Now this doesn't actually look like a fraction, but when we did integrating trig functions, we never looked at how to integrate tan. Well, tan, if you recall back from the trigonometry unit, is equal to sine over cos. So we're going to rewrite this as 3 sine 2x over cos 2x. dx. And then I think, well, what does cos differentiate to? Cos differentiates to negative sine. That is on the top, albeit not quite the same. So we're going to do those same steps. Rewrite that 3 sine 2x to the side, times by 1 over cos 2x dx, and then I'm just going to integrate that fraction. Leaving the first bit by itself, 3 sine 2x. Integrating that, we get times ln cos 2x plus c, and then we've got to divide by the derivative of the bracket. The derivative of cos 2x is negative sine 2x, and then I've got to times by the derivative of that bracket, timesing by 2. That's a revision of the chain rule. The signs cancel. We're left with 3 over negative 2, which is negative 3 over 2 ln cos 2x plus c. Number 4. Sometimes we can get these and they're a little bit harder to see at first. And number 4 is an example of this. We see it's a fraction, but the derivative of x ln x is most certainly not 1. But I know that the derivative of ln x is 1 over x. And there is a 1 over x in here, so maybe I can rewrite it with 1 over x on the top. To do that, we need to recognize that 1 over x ln x is the same as 1 over x times by 1 over ln x, which is the same as 1 over x divided by ln x, which means that this is integrate 1 over x all over ln x dx. Now we have it in the form where the derivative on the bottom is equal to the top. So, same as before, re-put that 1 over x over there, times by 1 over ln x. Then we can integrate. We get the 1 over x from before, times by ln of ln x. So we're timesing, so it's ln of the bottom, and then divided by the derivative, divided by 1 over x plus c. The 1 over x's will cancel, and we get ln of ln x plus c. Now you don't have to do this bringing the numerator to the side step if you can just see what the coefficient will be. I'm just putting it over here if it helps you to figure out what that coefficient will be. Number 5 looks a bit tricky, but it's a fraction, so most likely it's going to be some sort of ln integration. If I differentiate that cos 2x, I'm going to get negative sine 2x. And if I differentiate negative sine 2x, I'm going to get negative cos 2x. Of course, timesing by 2 for both of those. Those can be multiplied by something to give the numerator. So this is a log integration. Same steps. Bring the numerator to the side just for now. Times by 1 over cos 2x minus sine 2x. And then we're going to just integrate that section there. We get the cos 2x plus sine 2x times ln of cos 2x minus sine 2x. And then we're going to divide by the derivative of that bracket plus c as well. Cos 2x differentiates to negative sine 2x times by 2, and minus sine 2x differentiates to minus cos 2x times by 2. On the denominator, we can factorize out a negative 2. That gives negative 2 out the front, leaving sine 2x plus cos 2x times ln of cos 2x minus sine 2x, and cos 2x plus sine 2x on the top, sine 2x plus cos 2x on the bottom, they are the same. giving us negative 1/2 as our coefficient. Okay, so those are our quotients, but we can also get products. If you get a product that's in the form a derivative times a function, then we can sort of do the same thing as before. We can integrate the main function and then divide by its derivative, and they'll give us our answer. Now the first one's sort of like that, but it's a bit of a simpler case. The derivative of the bracket is just 2, and so this bracket has been times by 3, and so I can times 2 by something to get 3. So when I integrate this, I'm just going to leave the 3, increase the power of the bracket by 1 to get 6. And so we're sort of undoing the chain rule here. So when we did the chain rule with brackets, we times by the power, then we rewrote the bracket, reduced the power by 1, and then times by the derivative in the bracket. To reverse that, we're going to increase the power by 1, divide by the new power, and divide by the derivative inside the bracket. Now, that's like times it to the bottom. The derivative of 2x plus 1 is just 2 plus c. And so we get 3 over 12, which is 1/4. And so that's sort of exactly the same as normal integrating of power functions, but with a bracket. Number 2, we've got a little bit more complicated. We have a 5x squared times an e to the power of x cubed. So you've got to look at this and think, what is more important? Well, we know that when we differentiate e's, the e part stays there, which means the e must be more important. So I'm just going to look at this part here, and I'm just going to integrate that, leaving the 5x squared by itself. So I'm going to rewrite the 5x squared. We'll integrate e to the power of x cubed. Well, that's like leaving the e and then dividing by the derivative of the power. The derivative of the power is 3x squared. And the x squareds will cancel, leaving 5/3 as our coefficient. Now this method only works if the thing that's been multiplied is its derivative. If when you do this and the other variable does not cancel completely, then this is the wrong method, or you've made a mistake. Number 3, well, I look to see if there's any brackets. Now, apart from the angle, there's no brackets obviously here, unless we remember that cos cubed means cos 2x all to the power 3. Now, when we had brackets, brackets have to be there, and they have to remain. In order to get a cos 2x all to the power 3, there must have been a cos 2x all to the power 4 in the original function. So we're just going to look at this and just integrate that bracket. So I'm going to rewrite that 8 sine 2x first, and then times by. We increase the power of this bracket by 1. We then divide by the new power and the derivative. Cos 2x differentiates to negative sine 2x times by 2. Well, look at what cancels. We've got the sine 2x's cancel. The 8 is on the numerator, and 4 times negative 2 is on the bottom, so that's negative 8. So all of those 8s will cancel, just leaving us with negative 1. We'll get the plus c. So negative 1 is our coefficient, meaning we have negative cos 2x to the power 4 plus c, which can be written also as negative cos to the power 4 2x plus c. Number 4, again we've got brackets. We look to see the inside of the bracket and see what is the derivative. The derivative of inside the bracket is 2x. That's what's on the outside. So this is again in the same form. So we're going to just write down that 2x, and I'm only going to focus on integrating our bracket. So that will be increase the power of the bracket by 1, divide by the new power, and divide by the derivative of the bracket. X squared differentiates to 2x, 5 goes to 0. And cancel terms, we're left with 1/6 x squared plus 5 all to the power 6 plus c. Question 5. Right, we don't have brackets apart from the angles, but cos is definitely more significant than 2x. If I look inside the angle of the cos, it's x squared plus 3. That will differentiate to be 2x, so it is in the form f dash x times function of x. So we're just going to focus on integrating that cos. Leave the 2x by itself. Cos integrates to sine, so sine x squared plus 3. Divide by the derivative of that bracket, divide by 2x. The 2x's cancel, and we're left with sine x squared plus 3 plus c. Finally, sec to the power 5x tan x. Now, this currently isn't in the form of any sort of derivative times by original function. But I can see that the sec is a higher power, so that's probably the most important thing. So then I think, well, what does sec differentiate to? Well, sec differentiates to sec x times tan x. So maybe I can rewrite this as, take one of those secs from the sec to the power 5, we get sec to the power 4x times sec x times tan x. Okay, now we have a function times its derivative. Before I move on, I'm just going to rewrite this as, in brackets, sec x to the power 4. So those brackets are really clear to me. And now I can integrate, just focusing again on the main function, which is the sec in this case. So what will that give? Well, in this question, I've got to increase the power by 1. So that will be sec x to the power 5. I'm going to leave that sec x tan x there for now. Then I've got to divide by the new power and by the derivative of the bracket. The derivative of bracket is sec x times tan x, of course the plus c. Those completely cancel, leaving a final answer of 1/5 sec x to the power 5 plus c, or 1/5 sec 5x plus c. It's really important when you do these questions that you very quickly identify what is the function and what is the derivative. And you're not going to be told if it's this type of question, but generally speaking in integration, if you get some sort of complicated looking quotient or complicated looking product, it most likely is. And so you've got to observe what is more important.